Our goal is to solve this differential equation. The very first question you should be asking is this a separable differential equation? So on the left-hand side, you have dy over dx, and on the right-hand side, on the numerator, what I'm going to do, I'm going to factor out y, and I end up with x plus 2, and between these two, I'm going to factor out the negative sign. So you have minus, open parenthesis, x plus 2. The same on the denominator. On the denominator, between these two, I'm going to factor out y. So you have y, parentheses, x minus 3, plus, and I'm just going to group these together as x minus 3. Very good. So dy over dx can be written as, I'm going to factor out x plus 2. So I have x plus 2, open parenthesis, y minus 1, y minus 1. And on the denominator, if you factor out x minus 3, you get y plus 1. So you have a y plus 1. Very good. So as you can see, you can easily separate these two into the following. Dy times y plus 1 divided by y minus 1 is equal to, here you have dx multiplied by x plus 2 divided by x minus 3 times dx. Very good. Now, since it's a separable differential equation, we can take integral of both sides. It is a separable differential equation. So take the integral of both sides. So you have integral of, gonna use the same color now, y plus 1 divided by y minus 1 dy, and on the right hand side, you have the integral of x plus 2 divided by x minus 3 dx. We are going back to calculus. In the calculus part, we're going to separate y plus 1 over y minus 1 and write this as y minus 1 plus 1, and you have a plus 1 on top, and on the denominator you have y minus 1. So see what happens here. This can be written as y minus 1 divided by the denominator y minus 1 plus 2 divided by y minus 1. So we just separated this fraction into the summation of two fractions. Very good. So let me just rewrite this guy. So you see 1. That's how we separate these two. And as you can see, the very first fraction becomes 1 plus the second fraction, which is 2 divided by y minus 1. So this is your very first integral. The integral on the left-hand side becomes the integral of 1 plus 2 divided by y minus 1 dy. With the same argument, you can construct the second fraction set as, let me write this guy down here for you. So if you want to take a look at this later, x plus 2 divided by x minus 3. See, I'm just adding and subtracting the same number, negative 3, on the numerator. I get x minus 3 plus 3, and you also have a 2 divided by x minus 3. Now with the same method, just separate these two fractions, and you get x minus 3 divided by x minus 3 plus 5 divided by x minus 3. So you end up with 1 plus 5 divided by x minus 3. So this guy on the right-hand side is equal to the integral of 1 plus 5 divided by x minus 3 dx. As easy as that. The integral on the left-hand side can be separated as the integral of dy plus the integral of 2 dy divided by y minus 1. On the right-hand side, you have the integral of dx plus, you can write 5 also outside the integral, or you can deal with this later, absolutely fine. There is no restriction. And at the same time, remember that when you have the integral of du divided by u, it is ln of absolute value of u plus constant of integration. Very good. So let's see what's happening here. We're going to use this method that we learned in calculus. So the integral of dy is nothing but y plus 2 times ln of absolute value of y minus 1. And on the right-hand side, you have the integral of dx, which is just x, plus 5 times ln of absolute value of x minus 3 plus constant of integration. Let me move this a little bit here to avoid any confusion. Okay, we are almost done, everybody. We're going to simplify this further, but how? You have y and you have ln. So on the right-hand side, you have x and ln. You can write this way. You get y plus ln of, based on the properties of ln, you get ln of y minus 1 to power 2. This number in front of ln can be written as the exponent of the quantity inside ln. And on the right-hand side, you have x plus ln of, you have absolute value of x minus 3 to power 5 plus constant of integration. Very good. Assuming that it's on the positive part and everything, every quantity, x minus 3 and y minus 1 are positive, you can get rid of these absolute value as well. Let us bring all ln's to one side. I'm going to take this ln and write it on the left-hand side and bring everything else to the other side. So y goes on the other side. So eventually I can use the properties of ln. So I have ln of y minus 1 to power 2 minus ln of x minus 3 to power 5. And on the right-hand side, I have x minus y plus constant of integration c. From the properties of ln, if you have ln of a minus ln of b, this is ln of a divided by b. So you end up having on the left-hand side ln of y minus 1 to power 2 divided by x minus 3 to power 5. And on the right-hand side, you have x minus y plus c. Again, using the properties of ln, y minus 1 to power 2 divided by x minus 3 to power 5 is equal to e, or Napier number, to power x minus y plus c. Very good. Y minus 1 to power 2 divided by x minus 3 to power 5 can be written as e to power x minus y times e to power c. And I'm going to take this guy and call it a new variable, like a new constant, sorry, like c sub 1. So what's happening here? The family of solutions of the differential equation can be written as y minus 1 to power 2 divided by x minus 3 to power 5. On the right-hand side, you have c1 times e to power x minus y. So this is the solution, family of solution of this differential equation that you have here. So let us recap what we did. This is the differential equation that we have. This is a separable differential equation. Why? Because we can separate these. On the numerator, we factor out y. And here we factor out negative sign. And on the denominator between these two, we factor y. And between these two, we just group these together. So we could write this as the multiplication of x plus 2 times y minus 1 over x minus 3 times y plus 1. So now we can separate this by moving these expressions to the other side. On the left-hand side, I kept dy and then multiply y plus 1 by dy and divide by y minus 1. And I took dx and then multiply right-hand side by dx. So as you can see, it's a separable differential equation. You can take the integral of both sides. But to take the integral of both sides, we have to separate these into the fraction form. Y plus 1 divided by y minus 1. I'm just taking this number, negative 1, and write it on the numerator. But at the same time, to balance this, I have to add that number as well. And you have a plus 1 as well. So you just copy everything. Your goal is to simplify the first fraction into 1 and keep the second fraction with just one expression on the denominator. We did the same thing for the second fraction set as well. So we just took negative 3 and wrote it on the numerator, but to make sure we balance the whole thing, we add 3 as well. It also has constant 2 on the numerator. So our goal was to simplify this fraction into 1 plus the second fraction with just one expression on the denominator. It makes life much more easier because we know the integral of du divided by u is ln of absolute value of u plus c. The very first integral is y. The second integral becomes 2 times ln of absolute value of y minus 1. On the right-hand side, the integral of dx is equal to x, and the 5 times integral of dx divided by x minus 3 becomes 5 times ln of absolute value of x minus 3 plus c. Now we brought ln's to the left-hand side and wrote the rest of the terms on the other side. Why? Because we want to use the properties of ln. ln of a minus ln of b is ln of a divided by b. So the combination of these two ln's is equal to ln of their quotient. On the right-hand side, you have x minus y plus c. Using the properties of ln, ln is equal to log with base e. So you can write ln of the quantity equals to x minus y plus c as just the quantity equals to exponential e to power x minus y plus c. Now, since you have addition between elements on the power, you can separate this and you have e to power x minus y times e to power c. And I'm going to relabel these as C sub 1. So the family of solution of the differential equation is written this way. Implicit solutions of the differential equation